Great. So thanks for introduction once again. And the topic of this presentation is how to improve LatticeFold with L2 nonchecks. And it's actually very interesting that all of us are talking about nonchecks, and these nonchecks doesn't require a lot of soundchecks. So yeah, I find it very exciting. Okay, so again, what is folding scheme? If you don't know at this point, folding scheme, I just start with like stating out properties. So this is an algorithm which is turning relations into. Sorry, okay. This is very blinking, this screen. Okay. Anyway, so that is turning a pair of relation into some one relation that we call an accumulator. And also on the top of correctness, we defined extractability. That is is it possible maybe to turn? I mean, just can you turn it off because it's blinking. Okay, yeah. Then, yeah, just turn it off. I don't need it. So on the top of this correctness, we also talk again about this knowledge soundness or extractability. That we have some algorithm that we call an extractor that on observing the output statement, it outputs the input statements with some relaxations. And we also talk about succinctness, so we want to have fast verifier and small communication. And we again operate in this language of reductions of knowledge. So the reduction of knowledge is a pair of algorithms between prover and verifier that is reducing the relation xi0 to some new relation xi1, which are potentially different. And we, again, for this reduction of knowledge, and we view the folding scheme as a composition of reduction of knowledge, we define the regular properties like correctness, and also we talk about extractability of or knowledge soundness of this reduction of knowledge. So what is the relation that we are mainly interested? So in this talk, I'm reducing my focus again to R1CS, so that we have some matrices that are capturing our real natural constraints, and this relation in this case we defined over our cyclotomic rings. I present this because I want to give some vibe what we are talking about, some real life computations. However, practically in our lattice-based schemes, we talk about simplified linear relation, so that we have some witness which is committed under some I-type commitment, and on the top of that we define the constraint that, oh wow, that's fancy, that is a constraint over the multilinear extension over the witness. So we want that so that the witness evaluated at some point evaluates to some point S. So more pictorially, we look at this I-type commitment, and we view those multilinear polynomial evaluation as simply one row of additional constraint, and we will take advantage of that perspective. So the reduction from this R1CS to this linear relation, it's existing in the literature, and this I don't know to talk in this presentation, and also as David said, it all bases on hypernova. So what is the construction of lattice-based folding scheme? So in this previous presentation, I already introduced this graphic, so let me just try to capture again what we are talking. So we have this step of linearization that we turn this R1CS or any real-life constraint into a linear constraint. We have this homogenization, which makes them look similar, and then we are doing random linear combinations. Yes, and then we have the accumulator, which simply goes as an input for our next round of folding. And this all was covered in the previous presentation, so I'm skipping some time on the preliminaries. So now we have some problems that when we when we look at this folding, then of course this norm so we start from some norm beta, and after folding we have some norm beta prime. And this norm beta prime is could be larger, and it grows further and further with the rounds of folding. So to look again at this framework that we are building, like the traditional solution, and this time we are more traditional, we apply decomposition, which is just some solution. And now, for example, if we decompose into two relations, now our accumulator becomes two relations instead of one. And now, if we take a look again at this folding, and now pay a particular attention to this extraction process, we observe that if we start from the witness of norm beta, then here we are getting witnesses which are, we cannot even say that they are low norm, because actually, due to this rewinding, we can think that those witnesses are actually now equipped with some short denominator. And now we are talking not, this is our, we call it weak or relaxed relation. And yeah, so this additional denominators also will grow in this extraction process. So we are looking for some norm upgrade strategies. So in LatticeFold we have some strategy which is based on sum checks. In LatticeFold Plus uses also sum check, but with some more particular decomposition that is based on some monomials, which turns out to be particularly efficient. But all of those strategies seems to be inefficient due to the fact that they are relying on this L infinity norm, which is like, so all of those efficiency of those protocols scales up linearly with that norm. So essentially we are restricting our focus to very low norm relations. So here comes the open question which I would like to present answering this talk. Can we design a verifier and communication efficient range check which is particularly suited for L2 norm? So, of course, the answer is yes, because that's why I'm talking. So, the main tool that we will be using is Johnson-Linderstrauss projection, which is partially derived from Labrador. Labrador is a snark, is a lattice-based snark, and this lemma says more or less that if we take a matrix, if we take our witness W and then multiply with and do like a left multiplication with some projection matrix that sometimes we can call just Johnson-Linderstrauss matrix, then this multiplication, even under modular arithmetic, more or less preserves the norm, and up to some small statistical error. However, how it was done in Labrador, it was done with completely ignoring verifier efficiency. And if we would like to directly take advantage of this approach of Labrador, what would happen is that we have this our I-tie relation with potentially commitment and some additional constraints, and we simply swap this matrix at the bottom. It has the problem that now this verifier has to sample this matrix because it comes from the verifier in the interactive setting, or it has to be derived from the hash. But the verifier will sample and also further operate on this very large matrix, which is potentially linear with the which is just linear with the witness dimension. So here comes our approach that is also built on one of my previous works, that instead of thinking about this like a very large matrix, we can turn it into a many projections, each of them being with the same matrix. So now each of this projection can be said to be relatively small. But now we have a problem that, okay, since we are created many of those projections, potentially as many, so that operating on each of them is efficient, then we have to send it. Like, of course, this is not even a protocol at this point, but I already try to point to the issue that is coming up. That now the projection, assuming that this Johnson-Linderstrauss projection is reducing only by some constant factor, then this projection is very large. But now the idea is that instead of having one relation, we look collectively at many relations, so that we don't fold one relation, we fold L many relation, for example, two of them. And now these projections, instead of sending them, we can commit to them again. And then we can we can certify the consistency of between the projection image and the projection pre-image via some, well, in our work via some check, but this can be done via some, this is just some linear constraint that we have to certify about. And now, what happened, we introduced before our folding one more protocol that we call the projection, and this projection is spawning now this extra relation that captures the projection image. Now this projection image cannot be folded. It cannot be folded because we want to have an exact norm guarantee about this projection, so it simply serves as an additional relation in our accumulator. So now instead of 2 relations, we have 3 relations in the accumulator. But this norm is, still acceptable. So you may ask, are we done? Are we just solve the range check issues? Almost. The problem is that the additional complication is that now this Johnson-Lindenstrauss projection, it certifies about the norm of the witness only up to some constant, and the constant is very small. But when we talk about composition of this protocol, it actually will grow. So yeah, so we have a folding scheme. We will have the accumulator, and now in this extraction we will have also some growth. So if we would have, so even if this is like a constant across 1 folds, now if we would have composition of many folding schemes, like many times we analyze correctness and many times we analyze extraction, we will end up actually in the exponential loss. So to get an even tighter norm bound, the idea is that since we already know that the witness is more or less short due to this Johnson-Lindenstrauss argument, we can further argue about the inner product of the witness. And if we take a witness and the conjugation of the witness, we observe that the algebraic trace, or in the case of power of 2 cyclotomics, simply the constant term is holding the squared norm of the squared 2 norm exactly. So the idea is that we give an opening to this inner product on the top of proving about Johnson-Lindenstrauss projections. And since we already know that the witness is relatively short, it is enough that we observe that even though we have an argument that is arguing mod q, then if this is so short, we can just ignore this mod q, and we can simply argue about this exact L2 norm. So now we write it as a sum check. Sorry, when I did this talk, I didn't know that sum checks are not cool anymore. So we write it as a sum check and simply execute this and reduce it to the evaluation claim of the witness and conjugation of the witness. And now, since we have this, since we have those, the evaluation claim, the verifier just sends the evaluation claims of the witness and conjugation of the witness, add-on prover, verifier checks consistency, and now we have just some more things to prove. So we have to prove about this evaluation over the witness, about the conjugation of the witness, where we can simply the latter swap into the evaluation over conjugated points of the witness. Okay, it doesn't matter. Verifier can do it, prover can do it. But so now we simply have again one more claims to be proved. So now let's look at our image of this protocol that we're designing, and now before projections we are adding this inner product check, and this way our extraction is tight, and we argue about the exact norm of the witness, which doesn't propagate within many rounds of the protocol. So one more trick, of course, if we do sum checks, for example, in this homogenization in inner product, we can batch those sum check into a single protocol so that we have only one round of sum check, and we're done. And with those tricks, we design a folding scheme which replaces the expensive non-check of LatticeFold Plus, but also LatticeFold with the 2 steps L2 non-check. And asymptotically, we remove the dependency of the prover and verifier on the norm. And I expect that, at least this is what my initial estimation says, that this gives around 10 to 20 times speed up for the prover. And my estimations about the proof size is that it remains more or less the same as it was in LatticeFold Plus. And that's it, and thanks for listening.
Thank you very much, Michał. So are there questions? So maybe I try one question. So you say you eliminate the dependency asymptotically. So
yes,
completely. So like it's constant time from the point, like so.
So yeah, when I say about the asymptotic dependency, I mean like asymptotic dependency of the norm of the witness. So the runtime of the protocol technically doesn't depend on that. Of course, this dependency still comes to still plays when we set the hardness for our I-type commitment, because this depends on the norm of the witness. But except of that, the dependency, the norm is like unrelated to any efficiency measures of the protocol.
Okay. So if there are no more questions, we'll move to the next talk. Unfortunately, so thank you very much. So let's thank the speaker again.